Hello and welcome to the third part of Techniques for Self-Driving Cars. In this part we will talk about perception for self-driving cars. My name is Behley and I will present this part of the lecture. In this part we are specifically focusing on vision-based approaches, but we will talk also about the perception stack per se. But before we start, let's have a look which information is needed for enabling cars to drive themselves. The most obvious thing that we are interested in are the other traffic participants, such as here, like marked in the red, the vehicles in the surrounding, such as cars, but also trucks. Besides these parts that are moving mostly on the street, we are also maybe interested in the location of pedestrians that are maybe standing on the side of the street, such that we can consider their state and their behavior in our planning approach and also in the control of the car. Here are some pedestrians shown in green. Besides these, we are also interested in bicyclists because they are also an important part of the traffic participants, which has to be considered specifically. Here is some bicyclists standing on a traffic light and waiting to pass the street. Besides these parts that are moving maybe on the street, on the side of the street, we are also interested in the location of traffic signs because they tell us where we can go and where we cannot go. And such traffic signs are highlighted here in the light blue bounding boxes. Apart from this, of course, here in the street scene recorded in Bonn, we also are interested in the location of traffic lights because the traffic lights tell us something about the lanes and where we can go and where we cannot go. And also the state of the traffic lights is of course interesting for us because we need to know when we have to stop in front of a red traffic light. Besides this information, we are also interested in some other information, which is maybe more not the location of specific parts, but maybe of the arrangement of the scene around us, such as the drivable space, which is maybe here shown in the purple color, such as the road surface. This space we can enter and we are allowed to drive on. But there are also some space we are not allowed to drive on, such as the sidewalk on the side, which we should maybe avoid, maybe but use in also for parking or something like this. Apart from this low-level information about drivable and non-drivable space, we are of course interested also in some high-level information. This high-level information includes, for instance, the lane structure of the street, such as shown here by this light purple. Here we are interested in the different lanes and maybe also in the function of these lanes, such as here the car lanes, but also this bicycle lane. Apart from this, in this fine-grained semantic segmentation that we are estimating here, we are also maybe interested in getting here the location of the poles, because they tell us something about that we cannot park there and that we have to avoid this. So as you can see from this single image, we need to extract a lot of information about the surrounding in the vicinity of the car that makes us able to drive safely and predictably. But also the information between the traffic signs here in this location and the high-level information about the lanes needs to be associated. In this lecture, we are talking about a perception stack and the different tasks that are associated with this. Some of these you have already seen that we want to maybe have bounding boxes for traffic participants, but also pixel-wise information maybe for lanes or something like this. And then we will give a short overview about the different parts that are involved in camera-based perception and in the different perception tasks that we want to solve when we want to drive with self-driving cars. But let's first have a look at the perception stack. Commonly, self-driving cars are equipped with a lot of sensors. So here are some examples shown from commercially developed self-driving cars, but also from research vehicles. And the common perception stack, so the main sensors that are used are the cameras, the LiDAR, and maybe radar sensors that are used in the cars. For the cameras, the advantage is that they are very cheap and they offer high resolution information that can be used to really accurately locate information in the images. apart from this, they are able to provide us also with color information, which is of course important when we want to distinguish something like a red light or a green light, but also maybe the state of the blinkers of the car in front of us. A disadvantage of cameras is that they can be affected by illumination. So that means if we have some bright spots like the sun that is blinding the camera, then we are not able to see anything. But of course, we need also some additional light when we are driving in the night, so that we can see still something. And this is maybe a disadvantage that we maybe can solve by another sensor. One common other sensor for self-driving cars is the so-called LiDAR sensors. So that are lasers that are firing laser beams in the surrounding and generating a 3D point cloud of the environment. The advantage of these sensors is that they're independent of illumination. So that means we can equally use them at day but also at night. They provide us precise distance measurements, which is of course an important part in the perception stack of self-driving cars because it enables us to keep distance to other vehicles or other traffic participants. The disadvantage of LiDAR sensors is that they are very expensive. So in comparison to cameras, there's an order of magnitude in the cost involved. The other disadvantage is that usually LiDAR sensors that are today available only provide maybe a mid-resolution. So that means it's in between cameras and the other sensors. Another important sensor that is also equipped already in cars is the radar sensor. The advantage of the radar sensor is that it allows us to not only measure the position but also the velocity information of vehicles or pedestrians in the surrounding. Despite this, it's also a major technology that is used in a wide variety of vehicles like airplanes or ships or something like this. So therefore, radar is also commonly already equipped in cars. The disadvantage of radars is that compared to cameras but also LiDARs, they only allow us to receive an image that has a very low resolution and is very sparse. It's also sometimes a little bit noisy. Other sensors in the perception stack include the ultrasonic sensors that are mainly used for parking or something like this. So this is also already equipped and already in cars. They allow us to perceive the near range of the car. But of course, the global positioning system allows us to globally localize the car. So GPS is an important part also to localize cars in the surrounding. The inertial measurement unit allows us to measure the velocity and acceleration, which we can then use to maybe use it as short-time motion estimate of the car when it's driving. But also the odometer, which is basically measuring the speed of the car, can allow us to get some information about the state of the car and how it's moving. So as you can see, there are a lot of sensors equipped in the perception stack or can be used by a self-driving car. These complementing modalities allow the self-driving car or the autonomous car to perceive the world with different sensors. And this complementing information allows us to gather this information in a more reliable way instead of relying on one single sensor. So the belief is that not a single sensor will enable self-driving. Maybe the combination of cameras, IMU and GPS, or maybe the combination with LiDAR sensors will enable this. But the sensor fusion is here the essential part. So here you have to aggregate the maybe contradicting information from different sensors in a clever way, such that it allows you to reason about the surrounding in your environment. And this is a really hard task. But this will be not covered here in the lecture. In this lecture, we are mainly focusing on the camera part. So that means we are talking about the perception using RGB cameras. Common perception tasks are, for instance, the classification, where we maybe want to classify images, maybe here as shown from traffic signs, into different classes. But apart from this, we are also interested in getting maybe the location of objects in the surrounding. And for this, we are talking about the detection. Another task that I also already touched in the beginning is the pixel-wise classification of information in an image. And this is the so-called semantic segmentation. When we are interested not only in distinguishing a class, but also distinct objects, we are talking about the instance segmentation. In recent years, there has been the progress towards integrating semantic and instance segmentation. And this task is usually called the Panoptic segmentation. Here we are not only interested in the semantic segmentation, but also combine it with the instance segmentation. So nowadays you will mainly see works that are tackling directly semantic segmentation together with instance segmentation in a single task. But before we go deeper into these individual tasks, we have to talk a little bit about the technology that enables this perception task. And for this, recently, or not so recently, so since 2012, since the success of convolutional neural networks in the ImageNet challenge, there are mainly convolutional neural networks involved. So nowadays, most of the perception tasks, maybe 99% of the perception tasks, are solved using convolutional neural networks when we are talking about images. And here in this lecture, we cannot give a full overview over all in parts that are needed to do training and the construction of convolutional neural networks, but we will give you a high-level overview such that you have a good overview over the individual parts that enable you then to maybe go deeper into the research papers and then understand them. So here we are only providing a high-level overview over CNNs. But the question is now, why are the convolutional neural networks such an important technique that basically took off since 2012? So there are several reasons why we are seeing such an interest in this deep learning area. The first thing was that at that point in time with ImageNet, where the first time datasets available that were gathered from the internet that allowed to train on large-scale data. And as we will see, because convolutional neural networks usually have millions of parameters, with this amount of parameters, we need also a lot of training data to train them. So this was one reason why maybe in 2012 there was the time ripe to get there. But the other part was also that when we want to optimize this a lot of parameters, we have to compute a lot of things in the networks. And for computing this, there was the success of using the compute capabilities by GPUs, because they were now programmable in a way that they can be used for doing matrix multiplication and such stuff. So this was the second reason. But for me personally, the most important reason why deep learning took off like this was the availability of code, and also the research community that developed frameworks to enable easily to develop deep learning approaches. So nowadays, for most of the papers, the implementations are available on GitHub. So if you're interested in some of the methods that we are discussing today and you want to try it maybe on your own images, you can just download here for most of the papers the implementation, and then you just try it for yourself. And this also enabled, of course, people to build up on the solutions of others, and this accelerated the progress much more. And the other thing that is important here to note is that there are a lot of research groups, but also later companies developed frameworks that enabled to plug and play together these convolutional neural networks or other neural networks in a way that it made it easy to make progress there. So there are maybe Caffe, Theano, Torch, and so on. Today, the main deep learning frameworks are maybe TensorFlow and PyTorch. These are the most majored and also getting over time updated and gain new capabilities over time. But now so much about the basics, basically why convolutional networks and deep learning is so successful. Now let's take a look at the convolutional networks. And because a convolutional neural network is based on convolutions, a short recap on how convolutions work here. So we have here an image, in this case a grayscaled image, and we have this image represented as pixel values. So here these are intensity values. And these pixel values are now convolved with a kernel, so the convolutional kernel K here. And this is achieved by sliding the kernel over the whole image. And when we are applying this kernel, then we apply this in a sliding window fashion. So that means we take this kernel, put it on the first pixel here, 200, and this neighboring pixels, multiply this together in a sum. So this pixel is multiplied by this kernel entry, so 176 by -1, 0 times 78, and so on and so on. So this will produce then 77 and -77 in this case. Then we take this kernel and slide it a little bit further, and then the next value is computed, which is then -71. And we apply this over the whole image in the sliding window fashion, and by this we are getting all entries that the convolution produces in the end. So one side note, in the beginning you saw that there was a minus, which is the traditional definition of convolution, but usually in the deep learning framework it's much easier to just use the correlation, so therefore we usually have here the plus. So that means we are not flipping the kernel in the end, but this doesn't make so much difference. The operation itself is basically the same. So, but instead of fixed values, what we are now interested in convolutional neural networks is basically to have learnable parameters, the so-called weights here. And these we want to adjust in such a way that the network can achieve the task we are wanting to solve from then. For the convolution, to note is that we usually don't have only single channel image, but multiple channels, indicated here by the different colors. So we have an image with, in this case, 4 input channels, and then the convolution, so the 2D convolution in this case, has then also 4 channels. So that means we not only have 9 weights, but 4 times 9 weights in the end, which we want to adjust. So that means the kernel is still sliding over the whole image, but it will account for all entries from the other channels of the input image that we are giving there. But important to note is, even though the image has now 4 channels and this has also 4 channels, the output of one convolution is basically just a one-dimensional feature map in the end. So that means even though we have multiple input channels, we get out only one output channel. In this case, we now used here the channel in the back. So this is usually the channel last convention. In frameworks like PyTorch or so is the channel first convention. So, and just one note here, in the future slides we will just put the channel in the front, such that it's more coherent to the main framework that we are also using here in the research group, which is PyTorch. So we have here the channel first notation. So when we are now talking about a convolutional layer, we are talking about a layer that has multiple kernels. So here we have here indicated by this, the convolutional kernel, and this produces this activation map. As I said, when we have multiple input channels, this will produce one output channel. So since we are not only interested in having one convolution applied to this input, we are applying now multiple kernels to produce here this output map. So that usually resolves in that we have a certain number of input channels, and we apply then the different convolutions, in this case C out times kernels, to get then C out times H times W. So this is usually the tensor notation that we are using. So we, in this case, this is then the output of the convolutional layer. So each layer consists of multiple kernels that apply to the input. Since we now have this convolutional layer, one important part of usually of a neural network is that we not only have convolutional layers, but in between we need a nonlinearity. In this case, This is called then an activation function that is applied element-wise on all elements of the output. And these activations are a nonlinear function, and therefore we are getting some interesting behavior of the convolutions, of the convolutional layer, such that we can use in learning very complex functions. One common activation function is the so-called rectified linear unit, which just sets all values smaller than 0 to 0. And then has just, this is the nonlinear behavior. Sometimes it's not desired that we have this, that values smaller than 0 are also set to 0, so we can have maybe something like the leaky ReLU, where we have a slight slope here, so that we're getting non-zero values also for negative values. But there are different variants that can be used. So, but an important to remember is basically in a convolutional layer, usually we have a nonlinear function that transforms the input in a certain way. The thing that we want to now achieve in convolutional neural networks is not that we only apply it to the initial resolution of the image, but that we are doing multiple layers of this convolution. So we are stacking multiple convolutional layers with nonlinear functions in between. And since we want not only to have a very small receptive field, we are doing something in between. But before we talk about what we are doing, we have to see what is meant by the receptive field. So when we apply a convolution on a certain input, then we are aggregating basically this information from this window in the feature map here. But what this means, if we now stacking multiple of these convolutions, is that when we are going one step further, that we are aggregating basically from this layer this information from before. So that means by stacking multiple convolutions behind, we can get a very large receptive field. So that means what this kernel sees from the input maybe is a very large area, and this information is then aggregated from this area. So the deeper we go, the more the layers see from the input from before. And this is something that we want to have because we want to maybe see large cars in the image, and therefore we want to aggregate this information in the convolutional feature maps in the end. But to further increase basically the receptive field, we can now use something that's called pooling layer. The pooling layers are also aggregating information, but aggregating this information such that the layer shrinks, the output layer shrinks. And by using this pooling operation, we're also getting the advantage that we have some translational invariance, so that we can have small shifts. And common operations are here the max pooling and the average pooling. So what does it mean to now apply pooling to an activation map? When we're applying max pooling, for instance, for this input here, so this is the output maybe from a convolution, and we have now a kernel size of 2 by 2, then in the max pooling, we are just looking in this window and take the maximum value from this window. In this case, when we are looking at here at this 4 values, then the maximum is 14. So the max pooling operation will return then 14 in this case. And since we are applying this in a stride 2 fashion, that means we are not shifting the window by 1 pixel further, but in this case by 2 pixels. We are getting then this window, and then the maximum from this window is basically 5. And therefore the output from the max pooling layer in this case would be 14.5. And when we continue this, we are getting then this output. And as you can see, by applying this max pooling operation, we are now shrinking basically the feature map. And therefore, when we apply then to this again a convolution, we will then have on this input a much larger receptive field. Instead of using pooling operations, so just the maximum, we can also use to get the downsampling behavior, basically strided convolution. In this case, we are not applying, like before, the convolution at every pixel, but maybe at every second pixel. And by applying this in a strided fashion, we then also see that the feature map reduces. And this can be used to downsample in between. And when we combine this in the convolutional network, we have convolutional layers that are producing feature maps, and then we are using downsampling operations in between to increase the receptive field. So effectively, this kernel maybe then sees a large part of the input image when we are taking into consideration where it takes the values from. And what you usually see also in the convolutional networks is that when we're doing downsampling, then we are increasing the number of kernels that we're applying. So that means here shown are basically the tensors resulting from the convolutional operations. And as you can see, when we are doing downsampling, we are maybe increasing the number of features that we're extracting. And when we now want to use a convolutional network in the end to do classification, we have to transform the output from the convolutions basically in the output that we can use for classification. And usually for classification, we're interested in using something like softmax, and therefore we need to produce C values for C classes, for instance. And the last thing that is commonly used in convolutional networks are basically the fully connected layers, which is basically just a matrix product. Therefore, it's also called usually the linear layer. So, and when we have maybe a feature map that has dimension C times H times W, what usually people do is that they are flattening this vector so that we are having a vector of size C times H times W, and then we can apply the matrix multiplication. And with this, we can then produce exactly the number of outputs values that we are interested in. So that means we have desired that we are getting from C-in channels to C-out channels, which may be the number of classes that we are interested in. We have to apply here a matrix that has C-in rows and C-out columns. For learning this neural network, we just have to optimize basically this very complex function. So you can now think of the stack of functions. So we had in each convolutional layer weights that we are interested to learn. So in the first layer, we have the input xi, and then some learnable weights. These are now here w1. This will give us feature maps. And applied on its feature maps, we then have the max pooling operations, which are basically parameter free. And then another layer that is taking this output and then produces another output. And then we have in the end, maybe here L3 is maybe the output from the fully convolutional, fully connected layer. And therefore, we are getting then a very complex function in the end. And usually in the literature, we are saying that the parameter of this function are given by theta. And what we want now to achieve is basically to learn all these parameters in a way that we are optimizing the network in the way that we are interested in. So that means we want to minimize the loss function. The loss function is the objective that we want to minimize. That determines basically what the network structure should learn in the end. And that might be, for instance, the output of the classification layer, such that we are having a very good prediction for the class that we are interested in. So common loss functions are basically the L2 loss for regression task and the cross entropy loss for classification. So the loss measures basically the difference between our output that we are generating and the target output that we want to learn in the end, such as maybe for a bounding box, that the bounding box corresponds to a car. So the loss function determines the difference between our prediction and our target value. And for the L2 loss, we are just, because it's a regression task, the output value is here a continuous value, and then our prediction is also continuous value. We are just subtracting it and taking the square of these values. For the cross entropy for classification, we are using here the so-called softmax. So the output of the network is basically C values where the largest value should correspond to the right class. So, and here, for instance, for the jth entry of this distribution, we want to have the largest value. So that means we are taking from the output fx the jth entry, and then we are applying the softmax on this, which is basically just the exponential of the output divided by the sum over all outputs. And when we just take the logarithm and everything into account, then this corresponds to this. And this is the so-called cross-entropy loss. So with this, we can now measure the difference between the prediction of a network and the target value. And with this, we can now learn. And learning usually happens using gradient descent. So we are computing now for this whole network the loss functions, and then we are interested in how to adjust the weights of each layer such that we are minimizing the loss. So the idea is basically, how do we have to change basically this weight such that we are minimizing the loss in the end. In this case, that might mean that we are decreasing a little bit such that the value changes in the end. And when we further decrease this value or increase it, we are further decreasing the value of the loss. And for optimizing this, there's a very clever algorithm that we're not covering here now, but is usually used, and you maybe should know about it. It's the backpropagation. So with this, we can basically backpropagate the changes or the gradients that we need to minimize the loss through the whole network, such that we know in which direction we have to adjust the weights. And this is the basic learning technique that is used to optimize this very high dimensional parameter space, because you have to think of this, that there are millions of parameters that we have to adjust. But we touched only here the parts that are mainly needed to understand the papers that we are giving out in the seminar. But there's, of course, much more theory and building blocks and best practices to construct convolutional networks. But this is not part of this lecture. So when you want to have more details on how to train or construct CNNs, we will provide some links in the descriptions where you can find further material. With this short discussion on the convolutional networks and the basic building blocks of convolutional networks, we are coming now back to the perception task. And for the first perception task, we are looking now specifically on the detection. Most of the detection tasks are interested in having as input an RGB image, and we are interested in having an output such that we have a bounding box. The bounding box can now be defined by either just the left upper corner, the height and the width, but also by the center and the height and the width, or just by the upper left and lower right corner. This is the output that we want to predict. But additionally to the bounding box, for instance here in this car detection task, we also want to have a confidence how likely or how sure that we are that this bounding box really contains a car in the end. And this is the so-called confidence score, and this is usually between 0 and 1. So we want to have an input, an RGB image, and then output maybe multiple bounding boxes with confidence values. And usually in modern object detection approaches, we are not only predicting for a certain class bounding boxes, but for multiple classes. So it might be also that we have not only the confidence score, but a distribution of our confidences over the different classes. Modern object detectors mainly rely on convolutional networks. And we can see two main paradigms here. One is the so-called anchor-based approaches, and the other the anchor-free approaches. I will now give some examples on these two parts, and we will have then also in the seminar more papers on this. But first, what is meant by an anchor-based approach? So for the anchor-based approaches, we have usually two different kinds of approaches. So first, we are the so-called two-stage approaches, which generates proposals based on some anchors. And these anchors are then, these proposals are then classified such that each of these proposals is get a classification score and maybe get a refined bounding boxes. The other kind of anchor-based approach is the so-called single-stage approach. Here in this case, we only refine and classify the anchors in a single pass. But let's now take a look at the two-stage approach. One of the first and most famous approach for doing object detection with convolutional neural networks was the so-called faster RCNN, which is basically an extension of RCNN and the fast RCNN. But this approach was the first one that combined all parts in a trainable pipeline such that we can train the whole part from the input to the output. So the first stage is that the same part that we had before. So we want to extract the features. So the feature maps in this case are here the last feature map, and by using multiple convolutions. To make it now an object detection part, we now need, because it's a two-stage approach, some region proposals. And for this, the faster RCNN approach used the so-called region proposal network, which just takes basically the last feature map and then produces from this anchor locations, or ranks anchor based on the objectness and then produces proposals. These proposals are then taken into account to get the part of the feature map from before, so they are sharing basically the feature map, and to then classify them. So the third part is then for each region to classify this. And then we have some part that does the classification, for instance here car, person, and bicyclist, in one part that refines then the proposal region. So, but first we are talking about the so-called region proposal network. So what is actually meant by an anchor and the anchor classification. So the region proposal network takes for each location on the last feature map anchor positions, in this case k anchor positions. So these are differently sized bounding boxes which have a fixed location and a fixed size. And for each of these locations, the network is then tasked to give something like an objectness score. How likely is that this proposal or this anchor is basically on an object? And furthermore, it enables us to regress a little bit offsets in the x, y, and width and height of the anchor position. So that means in the end, we are getting 2k scores, so because we have an objectness and a non-objectness score, and we have 4k offsets for each of these anchors. So this is happening for all location in the feature map. So that means we have a very dense sampling of the whole input image. So, and as the convolutions and the max pooling operations in between are basically corresponding to different locations in the input image, this enables us to rank basically the proposals in a way that we are hopefully have then the proposals based on the objectness scores such that they are on top of an object. The objectness and the anchor offsets are produced for each of the anchors, so there are maybe 2,000 anchors. And from these 2,000 anchors and these scored anchors, we then take only the n top scored anchors. And these are then the so-called region of interest that is used then for the second stage, which is the classification and the refinement of the proposals. In this stage, we are now taking the n top ranked anchor and take these to classify them. And for this we are using here basically fully connected layers and then produce output scores. One interesting question is now, since this network is basically fixed, so and this gets a fixed input and we have differently sized anchors, how do we transform basically the feature values that we're extracting here based on the proposal such that we are getting an input that is fixed for the region classifier. And for this case, usually the region of interest pooling is used, which is basically very similar to the maximum pooling, but here we are now having a arbitrarily sized region of the feature map, which is then indicated by h prime times w prime, which is smaller than the whole image. And for this, we want now to produce k by k inputs for our region classification network. And what we are basically doing is that for each entry here, we are taking the average over all entries here in this region. So we are just splitting up the h times w large proposal region, and then split this up in k equals sizes in one direction and also k equal entries in the other location. And then we are doing, in this case, maybe max pooling, but we can also use average pooling to aggregate this information. And this gives us then this k by k output that we need for our region classification approach, which then uses some additional fully connected layers to turn this into the classification score, but also a refinement of the initial anchor boxes. So to summarize, faster SCNN trains the region proposal network and the Roy classifier jointly, such that we can propagate basically all the information that we have in the classification given by the loss back through the feature extraction in the beginning. And the faster SCNN is also because we are now implementing everything on a GPU, able to do this in near real-time operation. But as you have maybe seen, the region proposal network is already providing some bounding boxes, in this case the proposals. So is there the second stage even needed? And this was exactly the insight that people had when they looked at this approach. So maybe we can do just everything in a single stage. And for this was one of the first approaches, the so-called you only look once or YOLO detector. Here we take also anchor locations, so we are splitting up the image in multiple regions, and then for each of these anchor locations we are producing again objectness scores and offsets. And for each of the cells, so we are splitting up the image here, for instance, in 4 cells in each region, we are producing cell scores, which are basically classification scores that can then be used together with the anchor objectness to get the final result. So in the end we have output here, which is S times, because we have B times bounding boxes, which are basically the anchor locations, and then K class scores. And then we can take the class scores together with the objectness scores to determine which is the anchor in each of the cells that has the highest score in the end, which we again can use for extracting the bounding box that we are interested in. So the objectness score plus this class score produces then the outcome that we are interested in. From the architectural point of view, this is just a normal convolutional network with multiple layers that produces then in the end, in the case of the example which was given on the Pascal walk, a 7 times 7 times 30 vector in the end, which is then used in a post-processing step to extract the most likely location of objects in the end. So the advantage of this is that we now only have to do one pass through the whole network and then not apply for each region individually a classifier in the end, but can do this in one step. So the thing is here now that each grid cell produces at most one bounding box because we have only one class score, which is combined then with the objectness to extract one bounding box. But the advantage of this is that we are only needing now a single pass through the CNN, so that we can even do classification up to 144 Hertz at that point in time. But the disadvantage is that we are now having only one outcome per cell is basically that we might miss objects that are very close together. So that means in comparison to the faster CNN approach, this approach is less accurate, but also misses objects that are close together. Based on these anchor-based approaches, which basically produces anchors and then classifies them, there were the second branch of approaches that use not the concept of anchors, but the concept of key points. In this case, we are using a CNN to produce these key points, something like the corners of the bounding box or the centers of the bounding boxes, and then a second post-processing step which takes these key points to produce then the bounding boxes. And by this, we don't have anymore this concept of anchors, which we have to score in a certain way and that are basically at fixed locations, but can now have these key point predictions, which we are using to construct the bounding boxes in the end. So one of the first approaches was this corner net, which exactly did this. For the bounding boxes, we are now predicting with the CNN 2 heat maps. We have a heat map for the top left bounding box, top left corner of the bounding box, and the bottom right corner of the bounding box. And what we want now to achieve is basically to find corresponding corners in this heat map such that we can construct a bounding box. But how do we associate now the corners here? And the idea was basically to not only produce for each pixel the likelihood that there's a corner located, but also a so-called embedding vectors, such that the embedding vectors of the corresponding bottom right and top left corner are basically very similar to each other. So that means the network, so the CNN, is tasked with the task to get for the top left, the lower right, confidence scores, how likely is that at this pixel location basically is a corner located. And the second task of the network is to produce at the same time embedding vectors which enable us to associate the corners together. And the part that we are not discussed now is because currently we're just producing always from this high resolution input one tensor that has a certain resolution. But we can only decrease the resolution of the features that we are producing. But here we are interested basically in features for each location in the image. So that means we have to take this information, which is very useful because we aggregated a lot of information from the image from the beginning, but we need to blow it up basically such that we can use this as pixel-wise information in the end. And for this we are using then the so-called decoder. While the encoder produces features from the image, this aggregate information, the decoder spreads it basically out to the whole image so that we get pixel-wise information in the end. And for the encoder, as before, for the downsampling we can use strided convolutions or pooling operations, and for the decoder we have then a so-called upsampling. So, but how can we achieve this upsampling? One simple and straightforward approach is that we are just copying the values in every second entry of the upsampled image, and that we are just taking then the nearest neighbors. So this is the so-called nearest neighbor upsampling. A more clever way for upsampling is the so-called transposed convolution. Again, we are just blowing up the image and just copying the initial values here. What we are now doing is not just copying the neighboring values, but we are applying here a convolution, such that we can then produce the intermediate values. So that means when we are sliding over the upsampled version of this initial image, our kernel, the intermediate value will then account for neighboring values by awaiting. And by this we can then produce an interpolated and learn the upsampling function in a way. So as you can see, it basically inverts the process of the convolution. with this upsampled and now pixel-wise information, we can now associate the corners together. So for short summary of CornerNet is that we now have an anchor-free approach which produces corner locations, so the upper left and bottom right, together with embedding vectors, and the similarity between the learned embeddings is then used to determine which points we put together to produce a bounding box. And as we have seen, a common approach to get this pixel-wise information is to use this encoder-decoder architecture. With this, I will now switch to the second task that we are interested in, which is basically semantic segmentation. To remind you again what we're interested in, so we have some input image, we have a convolutional network, and we now want to produce a pixel-wise output for the whole image, where we want to assign for each pixel of this output a certain class, such as shown here, that we're having the road surface, the buildings, but also the cars. So that means for each pixel ij, we want to produce a class label which is from 1 to k for each of the pixels in the image. And as before, we want to have a pixel-wise information, so we can again use this idea of an encoder-decoder with upsampling in between. One of the first approaches to do this in a clever way was the so-called UNet. So we have here the encoder structure and then the decoder structure that produces then the output segmentation map. But interesting to note is here, what the people notice is that by doing the decoding, we are losing a lot of information and we are getting very blurry and insufficient results in the end. And this was solved by the so-called skip connections. Here we are taking the features from the encoder and just copy it to the decoder and then use convolutions to aggregate them. So we are concatenating the features from the encoder and then do the upsampling and then have an additional convolution on top of it to then aggregate the features together. And by using this, we are getting much better results in the end. So this is the most prominent approach to do semantic segmentation, is basically that we have an encoder-decoder architecture and then use skip connection like UNet. For the last task, the so-called panoptic segmentation, we have now to combine basically something from the semantic segmentation, but also maybe ideas from the detection. Because here we are not only interested in the pixel-wise classification, but also the distinction between different instances. So again, for panoptic segmentation, we want to have the pixel-wise classification, but additionally we want also to distinguish between pixels from different instances. In this case, these instances are called thing classes. So the stuff classes are usually classes that are not really countable or where we can easily identify object boundaries, something like sky, or maybe here these buildings, because it's not so clear where one thing starts or the other ends, or like the road surface. And for the thing regions, we are interested in distinguishing different instances. So that means we want to have here this instance mask, which assign each of the pixels from cars basically to a distinct car in the end. So, and by combining this, we are getting then the information that we're interested in, basically a pixel-wise classification that tells us something about the class of a certain object in the image, but also for the thing classes, basically the boundary of these things in the image. And this is the so-called panoptic segmentation. So for panoptic segmentation, we usually have two variants, which, as I said, combine in the top-down approach the part from the detection that we have bounding boxes, and then we are producing instance masks from these bounding boxes. But there is also this bottom-up approach, which are similar basically to the ideas that we also had with CornerNet, that we are producing first some vector space representation, which is then used for clustering in the end to assign pixels to individual instances. So therefore, we are getting from pixel-wise information by clustering then to this information that we are interested in. So these are the predominant approaches for doing instance segmentation. Just a short example of a network that does both together, so the Panoptic DeepLab, where we have a semantic branch, which is basically using the output of an encoder, then produce semantics in pixel-wise manner. So we have this semantic branch, and then we have this instance branch, which produces center predictions, similar to the way that CornerNet did it, but now specifically for the center location, and then the so-called center regression, which I will discuss in the next slide. But both together, the centers and the center regression basically allows us then to group the pixels into instances for the so-called thing classes, and then with the semantics together to build the instance mask that we are interested in for the thing classes. And at the same time, the semantics that we're interested for all the classes, basically for things and instances, but only the class assignment, which is provided by the semantics branch here. For the instances, as I said, we are not only producing the center location of the potential object or instances like the cars here, but we are also having this center regression. And the center regression produces now for each pixel of one instance vectors that should point towards the center location. And using this information, we can then cluster together the pixels that are pointing currently in the same location to get the instance mask that we are interested in. At inference time, we can then use this both together to cluster the instances, as in this case here. So to summarize, in Panoptic DeepLab, we have a shared encoder because we can use this information that we aggregated from the image for both tasks, semantic but also instance segmentation. And for instance segmentation, we are using again the center and center offnets to do a button-up clustering of the instances. And then the aggregation of semantics with the instance mask allows us then to distinguish thing instances in the image. With this, I want to come now to this part where we talked about perception tasks, and now maybe talk a little bit more about the high-level ideas. So the one important part that you may have noticed here is that we need for everything basically labels. So we are using mostly supervised training. So that means we need accurately labeled data. There are several research data sets available, such as Kitty, NewScenes, and Waymo, but also company produce with dedicated teams a lot of annotated data. And this is basically also one thing to note here. So we need a lot of annotated data. For some examples of common object detection data sets are given here. So the most famous one is maybe the Kitty dataset, which was produced in 2012. But we also recently see increasing data sets that were produced also by companies active in the self-driving area in the recent years. So as you can see here, one of the largest data set is maybe the Waymo Open dataset, which is produced, gives you 200,000 images. And usually they provide bounding boxes, but sometimes also segmentation masks. For tasks like semantic segmentation or panoptic segmentation, there are also some data sets available. But here the amount of labor that is needed to label the data is, of course, much more higher, and therefore there are not so many data sets as for the detection task available. But one of the most famous or the earliest data sets was the so-called MS-COCO data set, the common objects in context, but also the Cityscapes data set, which provides semantic segmentation, but later also panoptic segmentation for different cities in Germany. So if you're interested in semantic segmentation or even panoptic segmentation, then you can have a look at these image data sets. So as I already mentioned, labeling data is very expensive. And when we take a look at the time that is needed to produce such semantic segmentation data sets, then we can maybe also value the effort that companies and people invested in annotating such large data sets. Some examples here, as reported in the image, one annotator for such cityscape images basically needed 1.5 hours to annotate the whole image. So when we now take the number of images, which is in this case 5,000 for the finely annotated images, then we see that this took overall 7,500 hours, or something around, when one single person would do it, maybe something like 312 days, when he was only labeling the whole day and every night. For the Mapillary Vista dataset, when we take it again the same 1.5 hours per image, then this allots for the 25,000 images to something like 4.5 years. So where you can see that there must be a lot of people involved to annotate this data. Otherwise, they would not have been able to provide this data. But when we then look, for instance, for the MS COCO data set, there the authors report that alone labeling the categories took them something like 22,000 hours labeling overall. So they had a large set of annotators that annotated these. And then for the instance spotting, so that assigning instances to this, or figuring out where instances are located, this took additionally 10,000 hours. And when we then take together the instance segmentation, this comes then together to 26,000 hours. And when we compute everything together, then this is something around 6.6 years overall. So that means annotating such large data sets is also very expensive, because you can only achieve if you have a lot of people available to label such data. And of course, in this time is not included that also someone has to look over this data and to validate this and maybe correct errors. One other problem of this labeling a lot of data is that this is a never-ending task, because when we look at reality, or when you think about when you're driving around with your car, then you will see a lot of cars around. So getting training data for cars is very easy. So you just maybe drive around 1 hour and you will have a lot of cars. For pedestrians, this is maybe also true, or bicyclists. But when you now think, when you're driving around, how seldomly is that you are seeing somewhere some emergency vehicle, then the number of occurrences is very low. And when you now think about that you're driving around much longer, then it's very seldom that you maybe see a rescue helicopter maybe somewhere. So in this problem, that is the occurrence of objects or object classes in its surrounding, is called so-called long-tail problem, because we have many classes that might be also relevant for self-driving, that only occur very few. And we will not gather, maybe when we are driving around long enough, so much data points for the specific classes. So most of the classes appear basically in this long tail of the object distribution. So that means we will have something like construction vehicles, emergency vehicles, and so on, that are not, where we cannot so much gather so many images from as for other classes. And one important thing that is also occurring is that when we're driving around, then there will be some very rare events or situations that we also have to deal with. Something like this here, so it's a construction vehicle which is carrying traffic lights around. and maybe some of the workers forgot to turn off this red traffic light, and this car is now driving in front of us. And when you think of this, usually a car should stop when it sees a red traffic light. But in this case, of course, when we would stop on this highway then we would maybe provoke a crash in the end. In this example, for instance, we have a vehicle where on the back a stop sign is made. And usually also a stop sign indicates that we have to stop at a certain point. But in this case, because it's on a truck, the truck is just driving in front of us and the stop sign is moving. So what is now, the decision that the self-driving car should do. But also when we think about not only the situations that are rare, but also about the events that maybe also happen, that we have maybe people that are placing these bumper stickers all over the car, which maybe makes it also very hard to detect the cars. Here's one example maybe from Bonn, where we have a very dedicated football fan which covered his whole car with stickers from, I think it is Borussia Mönchengladbach. But anyway, so these examples, when you see them, are maybe, for you, maybe seldom. You will maybe not often see them in reality. But when you think about the scale that maybe self-driving cars are operating, then these rare events will not be anymore so rare. So the software that is basically on these cars is shared, and therefore it should also somehow react accordingly to this. So another example is maybe here, this truck that has reflection from other cars in the background, or maybe this guy that is maybe driving on the highway. So in all these situations somehow have to be gracefully handled. And one current research direction is maybe to handle such situation in a clever way by not only considering the classes that we maybe know, but also to consider the classes that we are not aware of. And this is the so-called open set perception. That means that not all relevant classes are known at training time. Here's, for instance, an example from Cityscapes. So in Cityscapes, the authors of the dataset have, of course, to make a decision. Which classes they have to annotate and which classes they are maybe not sure, or maybe they just leave out. In this case, they have this other pixel annotation, which basically indicates that they know that it's maybe a class, but they have no class assigned over one specific class. So that means these annotations are usually ignored by the semantic segmentation approaches or panoptic segmentation approaches in the learning. They are just mapped to some class like unlabeled and therefore will not turn up in the softmax as something that they have to classify. But in this case, as you can see, this is a baby stroller, and this is of course a class that should be recognized by a self-driving car and maybe taken into account, such that the car is maybe now slowing down because it sees that this lady with their baby is maybe passing over the street. So therefore, the classification that is maybe then predicted, because it's not included in the classification of the semantic segmentation approach, is in this case, for instance, that this is predicted as motorcycle, which is of course, maybe here, maybe something that is maybe makes still the car a stop, but maybe leads to an adverse behavior, so that it expects that this is maybe obeying the traffic rules or something like this. The same is happening here with a fashion stand, basically, where a store where people maybe would come out because they bought just something, and therefore the classification as just this building is maybe wrong, because it maybe have the adverse effect that the car is just driving by, because from the building usually no one is popping out when there's not a door or something like this. So that means an open set perception, we want to know also something about the things that we don't know at a point in time. So that means we want to learn or identify out of distribution samples or maybe anomalies. And one recent approach that achieved this was the so-called OpenGAN. So in this case, we are just taking a convolutional network as before, and we are applying this to so-called closed set images, so something like COCO, and then we have some outliers that are not present in the class distribution of COCO. And then what we want to learn is basically a discriminator that, based on the features, can then classify the image that we know from the training data from images that we don't know, the so-called open set. And this discriminator is then telling us something about when it sees something that it supposedly not saw before in the training set, such that we can react on this, or maybe take a snapshot of this image and maybe let someone label it or take a look at it. So we have this discriminator, but and we have this closed set and outlier images. So one problem with this is that the discriminator more likely overfits to just this example, such that it not reacts maybe to unseen open set examples, so unseen outliers. And one clever idea of the authors of this paper was, of this OpenGAN paper, was to include now here a generator. The task of the generator is to provide additional so-called fake features such that the discriminator has a harder job to distinguish closed from open images. And maybe learns in the end to be more robust for images that it had not seen before. So for outlier images that were not present in the training. And with this, the approach is then able to more successfully than other approaches to distinguish between things that it knows and from things that it doesn't know. With this, I'm almost at the end of this lecture. So some open challenges in perceptions, especially for reaching level 5 autonomous driving, that means no human is involved at all times, are of course the detection of rare events and situations, such that the car can react accordingly and gracefully in those cases. But also the integration, because now we are mainly seeing data sets with very sunny or very good weather condition, but what is when this weather condition changes? And this is basically the goal also of level 5 driving, that it can drive in any situation. And of course, what we also have to consider is that maybe people want to turn adversarial attacks, something like pointing a laser pointer at some cameras or something like this, on the perception systems. And the perception system in this case maybe has to register, okay, there's something happening and maybe I have to trust the information from some other sensor more than the information from the vision sensor. And these are effects that are very challenging and can need more research and more development also by the car companies. And the very important question is not only to detect or handle such cases, but how to deal with such situation in a way that is maybe gracefully and efficiently. Because maybe in such level 5 vehicles there will be no steering wheel anymore. So therefore the companies have to somehow figure out how to do this in the right way. But with this I'm also coming now to an end. So we looked in this lecture at the perception stack, but also on perception tasks, specifically vision perception tasks. We discussed a little bit about the CNNs as a backbone of most image-based perception, but also covered approaches for detection, semantic segmentation and panoptic segmentation. In the end, I talked a little bit about the challenges in visual perception and some open problems that need to be solved. And with this, I thank you for your attention and see you in the next lecture.